Recording has started.
好，那欢迎各位来到今天的 Terra Talk。那我是今天的主持人陈信达。那我目前是 University of Pennsylvania 的 Postdoc Researcher 在化学系。那我们今天很高兴，邀请到徐伟哲。那他目前呢是在 University of Colorado Boulder，就是博德分校。那在 Chemical Engineering 攻读 Ph.D。那伟哲他是2017年从台大化工系毕业，然后毕业之后就来到 Colorado Boulder，念化工的博士。那他今天要为我们演讲的题目呢是关于improved method for sampling the configuration space of flexible biomolecules。那相信这个是一个非常有趣的演讲。那伟哲，请分享你的 screen。OK， 然后Terra 的传统呢是我们会在会给讲者一个掌声。那欢迎请大家打开麦克风，然后现在请给大家给讲者一个掌声。
完全不知道原来有这样。
好的。
好，大家现在
好，我们可以看到你的 screen。
好，那我就直接开始了。Hello everyone， 对不起，我忘记讲那个，就是因为我觉得这个演讲就是我后来发现用中英夹杂的方式可能会有一点点难以解释这样，然后可能也不会比较清楚，所以我想了很久，我可能后来决定说我这场演讲会使用英文去讲这样子，然后但大家就是还是可以一样用中文提问这样子，然后如果有问题的话，那然后这个演讲我是想说，就是可能因为大家做的领域有点不太一样，所以我可能就是会以一种比较，我希望可能就是多比较偏重于概念层面上，然后少讲一些数学这样子。对，好，那我就开始我今天的presentation 这样。So hello everyone, my name is Wei-Tse. I'm a third-year graduate student from the research group in Chemical Engineering Department at CU Boulder. Today, I'm going to introduce you improved methods for sampling the configurational space of flexible biomolecules. 我发现我不能动投影片OK， 不好意思，可是可以用动画吗？好，可以，对不起。那我就直接从 outline 这边开始哦。As I know that the audience of this presentation might come from different fields, this presentation is aiming to give all the participants today a general idea about how we simulate flexible biomolecules and the underlying theories of available methods of doing that. Therefore, in the first section, I will be introducing the most commonly used advanced sampling methods that we use to investigate biophysical phenomena of biomolecules. Then in the second section, I will introduce the limitations of currently available sampling methods and how they motivated recent advancements in the field, including my own research work that is going to be published in the near future. So before we dive into the various kinds of advanced sampling methods, let's first talk about the general idea of sampling. In this slide, you can see an animated trajectory of a protein peptide binding complex, and that can be generated from molecular dynamic simulation. Each of the configurations you see in this trajectory can be regarded as a sample drawn from the configurational ensemble of the binding complex. Ideally, the whole configurational ensemble should be corresponding to the Boltzmann distribution of the molecule, which is a thermodynamic distribution of particles over energy states accessible to them. As you would imagine, each of these configurations you see in the trajectory typically has a different energy from each other. According to Boltzmann distribution, the structures with a higher energy would have a lower chance to be observed. Because each of these configurations corresponds to a probability, we can also say that each configuration is a sample drawn from Boltzmann distribution. Therefore, the process that we get these samples, namely a molecular dynamic simulation or a Monte Carlo simulation, is what we call as sampling in computational molecular science. And typically, the purpose of such sampling is to obtain the whole configurational ensemble, or equivalently, the Boltzmann distribution of the molecule that we are interested in. So why do we care about the configurational ensemble or the Boltzmann distribution of a biomolecule? This short answer, the short answer to this question is that with configurational ensembles, we will be able to answer questions that cannot be addressed by experimental methods. In this animation of the protein-peptide binding complex, the peptide is colored in blue, while the protein is colored in red, with four of its residues colored in yellow. From this animated trajectory, we could easily observe the dynamics of the system and tell that the peptide was restrained by the residues colored in yellow, so that the peptide did not drift away from the binding cavity of the protein. This is something that could be missing from experimental methods such as X-ray crystallography or NMR spectroscopy. As we all know, these experimental methods are limited to studying only one single snapshot of structure, and they fail to capture all the complexities or the dynamics of a molecule. For example, X-ray crystallography generates a single electron density map at a time, and the process could be very time-consuming. As such, predicting all the available structures or even a configurational ensemble of a molecule is typically very challenging using experimental methods. This is where molecular simulations come into play. In my research, I mainly use molecular dynamic simulations instead of Monte Carlo simulations. Molecular dynamic simulation is a general algorithm used to predict the 3D coordinates of each atom in the molecule as a function of time by numerically solving Newton's equations of motion given the initial conditions of the system. Ideally, using molecular dynamics, we should be able to get the configurational ensemble of the molecule under estimation, which is important in characterizing the binding affinity between the ligand and its receptor, or understanding biophysical phenomena. In a configurational ensemble, typically there are several metastable states. These metastable states are thermodynamic states that are particularly stable because they have low free energies. For example, for a binding complex, the metastable states would be the bound state and the unbound states, as you can see in the figure. Here is a simplified example of the host-gas binding complex where there was only one bound state and only one unbound state. To obtain the binding ensemble or calculate the binding free energy of such a binding complex, ideally, in a single simulation, we hope to see that the system is able to sample both the bound state and the unbound state for multiple times such that we can capture all the possible binding configurations and generate an ensemble that is representative enough. However, making the peptide bind and unbind for multiple times in a standard MD simulation is very challenging. In the animation, you can see that you can see a simplified example where a large free energy barrier can make it really hard for the system in standard MD simulation to sample both metastable states. From a statistical thermodynamics viewpoint, this issue could be interpreted as a result of insufficient probability overlap between these two metastable states. And to understand why the probability overlap matters, let's take a look at different cases. In the first case, you can see that there is a fair amount of probability overlap between the two metastable states, state A and state B. Therefore, when we draw samples from the probability distribution of state A, when running a simulation starting from state A, it is likely that some of the samples also belong to state B, meaning that we could get samples from both metastable states in just one simulation. However, for most biomolecular systems, this almost never happens. Most metastable states of biomolecules do not have probability overlap with each other due to the separation of the large free energy barriers. That is, starting from state A, we could only get samples from state B by a very, very small chance. This means that if we are running a traditional molecular dynamic simulation, the timescale will be much, much longer. To address this long timescale issue, various advanced sampling methods have been developed in the past decades. These methods manipulate principles of statistics and thermodynamics to accelerate the configurational sampling. Generally, we could classify these methods into two different types, although they sort of overlap with each other. The first type of advanced sampling methods rely on what we call as collective variables, which are low-dimensional functions of atomic coordinates of the system. They could be a distance, a torsional angle, or even a coordination number. Generally, a good collective variable should be able to distinguish different metastable states of interest and capture all the slowest degrees of freedom of the system. For example, for a host gas binding complex, the collective variables we could use to distinguish the bound state and the unbound states would probably be the distance between the centers of the mass of the host molecule and the guest molecule. Sometimes the orientation of the guest molecule or the host molecule of or the host molecule also might matter as well. So the most well-known methods of this type of advanced sampling methods are metadynamics and their variants. In addition to methods that are based on collective variables, there is another class of methods that do not rely on collective variables, but a series of intermediate states. These intermediate states are built to bridge the gap of probability overlap between the end states of interest. They could have different values of collective variables from each other as the ones used in umbrella sampling and its variants. They could also be different in temperature or Hamiltonians, like the ones used in replica exchange, expanded ensemble, and their variants. In this presentation, I will be introducing the most commonly used advanced sampling methods. Although there are several variants of each of these methods, due to limited time, I will only introduce the standard version of each method. And in the second half of the presentation, I will talk about the future of advanced sampling methods and present some of my relevant research work. So the advanced sampling methods that is conceptually easiest to understand is metadynamics. As you can see in an animation, in a standard molecular dynamic simulation, the system could be trapped in a certain metastable state. And to enable the system to cross the free energy barrier, in metadynamic simulation, we could add Gaussian biasing potentials to compensate the free energy basins. As soon as the free energy basin trapping the system is still filled up, the system can easily cross the free energy barrier and reach another metastable states that we are interested in. If we deposit a Gaussian biasing potential at every certain period of time, then the total added biasing potential at time t can be expressed as the equation you see in the slide. As you would imagine, given sufficient amount of time, all the free energy barriers can be filled up by Gaussian biasing potentials. At this point, the free energy surface would just be the negative image of the total added biasing potential. Therefore, the crossing of the energy barriers allows us to sample different metastable states and calculate the free energy surface along the CV direction. Another well-known method that relies on a collective variable is umbrella sampling. However, instead of modifying the underlying free energy surface of the system, umbrella sampling utilizes a series of intermediate states with different values of selected collective variables. To understand how umbrella sampling works, let's first take a look at a very simple example, a sodium chloride. So there are two apparent metastable states of a sodium chloride, which are its associated states and its dissociated states. And as you would imagine, the biggest difference between these two states is the distance between the sodium ion and the chloride ion, or what we call as the ion pair distance. As the ion pair distance, because the ion pair distance can well describe the slowest degrees of freedom of the dissociation reaction of sodium chloride, using it as the collective variable, we should be able to use umbrella sampling to obtain the free energy as a function of ion pair distance. Specifically, this is a two-step procedure. In the first step, or what we call as the pooling simulation, we fix the sodium ions and pull the chloride ion away. Along this pooling trajectory, different ion pair distances, or we can say different values of collective variable, correspond to different structures. From these numerous structures, we select a specific number of configurations where there are enough probability overlap between adjacent states. Then we perform a normal ND simulation for each of them. In the second step, which is the standard ND simulation for each of the configurations, we use the harmonic biasing potential to restrain the chloride ion at its corresponding value of collective variable. By doing so, we can force the system to sample the thermodynamic states of certain values of collective variable. After finishing all the simulations for each of the simulations, we can calculate the probability distribution of the collective variable. Given sufficient probability overlap between adjacent states, we can use statistical methods such as WAM or M-bar to stitch all these distributions and calculate the free energy profile of the sodium chloride. In the previous slide, I've just presented a very simple system where the collective variable that dominated the lowest degrees of freedom was obvious. However, as you would imagine, for a lot of highly flexible biomolecules, defining collective variables based on intuitions or experimental observations could be very challenging because the slowest degrees of freedom tend to be very complex. Unless we know pretty well about the system, methods relying on collective variables such as metadynamics and umbrella sampling won't be very useful. Alternatively, we can use another method that is called expanded ensemble, which relies on a series of intermediate states that are called alchemical intermediate states. Here we are considering a host gas binding complex as an example, and we want to calculate the binding free energy of this binding complex. Generally, to do this, we have to define a series of alchemical states. These alchemical states are defined by varying the values of alchemical variable lambda from 0 to 1, with 0 meaning that all the interactions between the ligand and the rest of the system are turned on, and 1 being those interactions are turned off. As you would imagine, by constructing this series of intermediate states, we can gradually turn off the non-bounded interactions between the ligand and the host, or the ligand and the solvent. Considering the host gas binding complex you see in the slide, we can see that these intermediate states could compose of a thermodynamic cycle. Given sufficient probability overlap between adjacent intermediate states, to calculate the binding free energy, we can simply sum up the free energy differences between the end states of each step you see in the flowchart. Since these states are useful for extracting the most information about binding free energy calculations, just like the modern alchemy, these states are called alchemical intermediate states. After understanding the significance of alchemical variable, let's take a closer look at the expanded ensemble method, which is a technique that relies on alchemical intermediate states. To understand the concept behind the reason that expanded ensemble utilizes alchemical intermediate states, let's back up a little bit to look at this free energy surface. So in a standard MD simulation, which is a simulation in the case that the alchemical variable is always 0, starting from point A, the system is not able to cross the free energy barrier to sample point C. However, we can see that at different lambda values, the free energy profile could be very different. That is, the free energy barrier we have at lambda being 0 might be absent at other lambda values, as you can see in the position of point B in the figure. Therefore, if there is a way that we can move from point A to point B and then point C, then we would be able to circumvent the free energy barrier between point A and C at lambda being 0. This is exactly what happened in an expanded ensemble simulation. As in an expanded ensemble, the sampling of the collective variable direction is done by a standard MD simulation, while sampling between different thermodynamic states is done by Monte Carlo simulations. As you can see, sampling the alchemical space apparently means that we have to cross the free energy barrier in the alchemical direction. And in an expanded ensemble, this is done by applying a weight G sub k, added to each alchemical states. And just like the Gaussian biasing potentials deposited in metadynamics, these weights modify the underlying free energy surface, allowing roughly equal sampling in the alchemical space. So once the sampling of all the intermediate states are equal, the weights are equal to the free energies of the alchemical space. Conceptually, to cross the energy barrier at lambda equals to 0, the system can just drift to other lambda states and then drift back. This is how the expanding ensemble accelerates the sampling between different thermodynamic states. On the line of using alchemical intermediate states, there is another advanced sampling method called Hamiltonian replica exchange that can be regarded as the parallelization of expanded ensemble. That is, instead of having only one single simulation sampling different intermediate states serially as expanded ensemble, in Hamiltonian replica exchange, there are multiple simulations running in parallel and exchanging Hamiltonian with each other. As an example, say that now we have 4 replicas starting from different alchemical states. For all the replicas, we use the alchemical variable to control the electrostatic interactions, van der Waals interactions, and a restraint. And for example, the alchemical variable of replica 1 is a 0 vector, meaning that all these interactions are remained on. While for replica 2, 50% of the electrostatic interactions have been turned off. And as you can see in the animation, with these 4 replicas, we exchange the neighboring replicas every n steps of the simulation. After several exchange attempts, some of them might be successful, but some of them might not be. And after all these exchange attempts, you can see that we exchanged the lambda. You can see that the lambda values of replica 1 becomes lambda 3, which is relatively closer to the uncoupled states. Ideally, given reasonable transition probabilities between alchemical states, all the states should be well mixed, which means that the system will be able to sample both the coupled and uncoupled states frequently in the simulation. This is exactly what we need to accurately estimate the binding free energy and generate a reasonable binding ensemble. So in the first half of this presentation, hopefully I've shown you the general ideas of most commonly used advanced sampling methods. However, as you might have discovered, these advanced sampling methods all have their own drawbacks, which motivated the recent advancements in the fields. So for example, as I have mentioned, for highly flexible biomolecules, the identification of good collective variables could be very challenging, which undermines the utility of methods relying on the collective variables, such as metadynamics and umbrella sampling. To address this issue, researchers have been trying to incorporate the power of deep learning to help select good collective variables. One of such applications is an algorithm called RAVE, or Reweighted Autoencoded Variational Base for Enhanced Sampling. This algorithm is an application of deep learning algorithm called Variational Autoencoder. One of the advantages of using RAVE is that it is able to naturally produce physically interpretable collective variable. In addition, it has advantages that it is independent of existing enhanced sampling protocols and can easily filter out spurious solutions learned by the deep learning procedures. So as I just mentioned, RAVE is an application of Variational Autoencoder, or VAE, which is one kind of variations of autoencoder. Therefore, to understand RAVE, we first have to understand what an autoencoder is. An autoencoder is a pretty popular tool to reconstruct a data set, such as an image or an audio. Typically, it is composed of an encoder and a decoder, which are both neural networks characteristic of a sequence of linear transformations. As you can see in the figure, given high-dimensional inputs such as a high-resolution image, the encoder network is able to map the high-dimensional input to a lower dimensional latent space, which is the so-called bottleneck layer. Then the decoder network will recover the data from the code in the latent space as the high-dimensional reconstructed input. After that, the autoencoder, as trained on the reconstruction laws, will compare the difference between the reconstructed input and the original input and optimize its parameters to minimize the difference. At the end, after the autoencoder is trained, the reconstructed input will almost be the same as the original input. Characteristic of data compression, this deep learning network has been widely used in the field of signal processing. And similarly, variational autoencoder is also composed of
Sorry, can I interrupt you a little bit?
Yeah, sure.
Yeah, so when you say train the autoencoder, you're training the encoder and decoder at the same time, right?
Yeah, that's right. Yeah.
Okay, so isn't that going to, let's say, isn't that going to cause some overfitting problem?
Yes, there might be some overfitting problem in in this kind of, yeah.
How severe is that, or is there a way to get that under control?
I'm actually not very sure. So RAVE, like the advanced sampling method that I'm going, no, it's not. I mean, RAVE is an algorithm that uses variational autoencoder to identify good collective variables, and I'm not very so. If my impression is correct, I think that there might be some measures that can be taken to um, to deal with the overfitting problem intrinsic in the deep learning network, but I might not be introducing that because that is kind of complicated, and I have to actually record some of the content of that. Yeah, but I remember that there is some measure taken in the RAVE algorithm to kind of solve this problem. Like it is able to like leave out the spurious solutions as a result of the overfitting problem, I think. Yeah.
Thank you.
So yeah. So just now I've just mentioned I've just introduced the autoencoder. So right now, let's talk about variational autoencoder, which is a variation of the autoencoder algorithm. So a variational autoencoder is also composed of an encoder and a decoder, or what we call as the probabilistics encoder and a probabilistic decoder. And unlike a standard autoencoder, which maps the input into a fixed vector of code in the latent space, a variational autoencoder, or VAE, maps the input into a distribution instead. Specifically, given the high-dimensional input x, the probabilistic encoder maps the input into two vectors, mu and sigma, which respectively corresponds to the mean and the standard deviation of a Gaussian distribution in the latent space, which is denoted as p sub theta of z. And then the probabilistic decoder samples from this latent space distribution and converts the samples back to the real space to recover the input data. Similarly, the variational autoencoder is trained on its loss function, which is the equation you can see in the slide here. The first term of the loss function is the reconstruction loss, while the second term is the KL divergence. So, which measures the distance between the approximation function and the Gaussian prior distribution in the latent space. And similarly, after the VAE is trained, it is able to reconstruct the input data. And understanding the architecture of variational autoencoder, now we can turn our focus back to the RAVE algorithm. And basically, the authors of this method chose VAE due to its aptness for learning reliable low-dimensional latent variable representations that can nonetheless capture the most important features in the original data. And that is, in RAVE, we start with running an unbiased MD simulation monitoring our trial collective variables as a function of time. Say that we consider k different CVs, then the input data set will be k-dimensional. Through the probabilistic encoder, these input time series are encoded into two vectors, which we can use to construct the probability distribution in the latent space p sub theta of z. After the decoder recovers the data from the samples drawn from the latent space distribution back to the real space, and the loss function is trained, the variational autoencoder is trained such that the loss function is minimized. After the variational autoencoder is trained, instead of focusing on the reconstructed input, we put our emphasis on the probability distribution generated in the latent space. Since this distribution, in principle, compress the input data and only preserve the most important features of the simulation trajectory. However, this latent space distribution compressed the input time series in a very complicated way, which is lack of physical interpretation. Therefore, instead of trying to interpret the physical meaning of this complex latent space representation, we instead compare this probability distribution to the distribution of the trial CVs, and we identify the CV that has the most similar probability distribution. That is, we use KL divergence to measure the distance between the unbiased probability distribution in the latent of the latent space and the unbiased distribution of the trial collective variables. The collective variables that has the closest probability distribution to P sub theta of Z is denoted as chi here, which is the CV that is able to best describe the main features of the trajectory. After a collective variable is identified in the first round of RAVE, we then run another simulation biasing this collective variable, chi, whose biasing potential can be easily calculated using the equation you see in the slide. And we want the simulation to be biased such that it is able to explore the configurational space more comprehensively. However, since the simulation is biased, which means that each MD data point is weighted by the exponential of the biasing potential, we have to reweight the probability distribution before we feed the data to the RAVE algorithm again. Specifically, we use the simple reweighting formula you can see in the slide to remove the bias. Then we feed the reweighted time series to the variational autoencoder. Again, with the reweighted time series, the deep learning network compressed the data to a one-dimensional probability distribution with which capture the important feature of an unbiased simulation even better than the previous run. And we again determine and update the optimal CV by minimizing the KL divergence to ensure physical interpretability of the CV. Then we use this new optimal CV to bias the next MD simulation, reweighted the data, and feed it back to the RAVE algorithm, and so on. That is, we basically repeat step 2 to step 5, iterating between the variational autoencoder and the MD simulation until the desired thermodynamic observable is converged. And to examine the power of RAVE, this method has been applied to a very challenging problem, which is the unbinding of a fluorine from the binding pocket. As you can see in the figure, the fluorine molecule is colored in red. The cavity atoms that interact with the ligand and with the water molecules are colored in orange, and the blue atoms are the wall atoms. This system is known by its very high energy barrier of unbinding as about 30 to 35 kBt, which corresponds to a timescale more than 3 minutes and requires an unbiased MD simulation of more than 1 million years, even with the best available supercomputing resources. And in this problem, 3 candidate CVs were identified. The first one is the vertical distance between the fluorine and the cavity, and the second one is the axial fluorine cavity separation, and the third one is the number of water molecules in the cavity. The first 2 CVs are more straightforward, while the third one might not be that straightforward. And the reason that we consider the number of water molecules in the cavity was because that for a lot of binding complex problems, water molecule might cause steric hindrance during the ligand binding or unbinding, which potentially leads to a pretty slow degrees of freedom. Specifically, when the ligand unbinds from the cavity, it might take a long time for the water molecules to go in and fill up the cavity. On the other hand, when the ligand tries to bind back to the cavity, it needs to exclude the water molecules first, such that there is enough space to accommodate the ligand. And the goal of this in this problem is to assess the importance of each candidate CV to determine the best one-dimensional CV as the linear combination of these candidate CVs. As a result, it was found that the variable Z had the largest weight, and the number of water molecules in the cavity barely influenced the unbinding event. And this implies that the distance between the ligand and the cavity is more dominant than the number of water molecules in this case. And most importantly, this example just shows that RAVE is robust enough to provide molecular insights, even if the energy barrier associated with the phenomenon we are interested in is very high. So I've just showed you that the difficulty of selecting collective variables. And as you can, so there are still other problems in the in other advanced sampling methods. So as I mentioned, the expanded ensemble method, I mentioned that using a series of intermediate states, it was able to circumvent the needs of defining a set of collective variables. However, expanded simulation also has its own drawback that the system could be trapped in the alchemical space if there is a very low free energy basin in that alchemical direction. So that is the reason we want to figure out a new method to solve that problem. And so you can imagine that if the system was trapped in the alchemical space, was trapped in the basin in the alchemical space, the easiest way is to apply Gaussian biasing potential to fill up that basin of the alchemical space and force the system out of that basin. And this is equivalent to applying Gaussian biasing potential to the alchemical space in metadynamics. And in this presentation, I temporarily call this method as alchemical metadynamics. So wait a second. I think sorry, I thought that I missed that slide. But so here is a more like schematic representation of the problems that I just described. So I'll just rephrase what I talked about, the problem of the expanded ensemble. And so in the figure, you can see that like it is possible that some of the regions circled in the free energy surface have particularly low free energies, which can easily trap the system, or like it is possible that the system is stuck because the energy barrier exists at all lambda values. And as you can see, even if the system could drift to other lambda states, there is still an energy barrier that is hard to overcome. So apparently these issues could be potentially solved by metadynamics if we are able to add Gaussian biasing potentials in the alchemical space. And as you can see in the animation, the biasing potentials added to the surface decreases the difference in the heights of different regions. And with this algorithm, we expect that the basins in the free energy surface can be filled up so that the system will not be trapped in any intermediate states. In the project that we've been working on in the past few months, we've been trying to develop such a method. And as I just mentioned, I'll just call this method as alchemical metadynamics. So in my presentation, alchemical metadynamics refers to any types of metadynamics that is able to bias alchemical variables. If the metadynamics only bias the alchemical variable, we call it as 1D alchemical metadynamics. This type of metadynamics is similar to expanded ensemble in the sense that they both apply weights in alchemical space to allow even sampling. The only difference between the two methods is the way that the weights are determined and updated. And just like any other types of metadynamics, we could add as many CVs as we want. In multi-dimensional alchemical metadynamics, we additionally bias the chosen configurational CVs. For example, by two-dimensional alchemical metadynamics, we refers to metadynamics biasing one alchemical variable and one configurational collective variable, such as a distance or dihedral angle. And that is, regardless the dimensions being biased, in alchemical metadynamics, the system jumps between the alchemical intermediate state through Monte Carlo simulation, which is aided by the biasing potentials added by metadynamics. If the configurational CVs are also biased, we apply Gaussian biasing potentials in the coordinate direction, just like what we do in any other types of metadynamics. And our goal in this project is to show that alchemical metadynamics can accelerate sampling better than expanded ensemble, especially in 2D cases. So to reach our goal, we implemented alchemical metadynamics. And given the similarity between alchemical metadynamics and expanded ensemble, the implementation was tested with 3 different model systems, with different alchemical processes by comparing the results of free energy calculation with expanded ensemble. Specifically, system 1 and 2 are an argon 8 and an lactic acid. These are produced from water, respectively. while system 3 is a host-gas binding complex in which the ligand disappeared from the binding cavity. That is, the free energy difference between the coupled and the uncoupled states is the Solvation free energy of system 1 and 2, and a part of the binding free energy for system 3. And to validate our implementation for each test system, we compute the free energy difference between the coupled and uncoupled states from alchemical metadynamics. Specifically, we compare these results with two values. The first one is the benchmark obtained from long expanded ensemble simulation, and the second value is the free energy difference obtained from an expanded ensemble with the same simulation length as the alchemical metadynamics. Particularly in system 2 and system 3, we introduced the configurational collective variable to see if the sampling was also was able to further facilitate it. And in system 2, the slow degrees of freedom is the formation and the distribution of the internal hydrogen bond. So we introduced the dihedral angle relevant to the hydrogen bond as the configurational CV. On the other hand, in system 3, we introduced the number of water molecules entering the number of water molecules in the binding cavity as the configurational CV, because as I just mentioned, the motion of water molecules entering and exiting the binding cavity typically is the slowest degrees of freedom for a binding complex. So with this configurational CV introduced to metadynamics, we hope to see that metadynamics can further accelerate the configurational sampling. So to calculate the free energy difference between the coupled and uncoupled states, we utilize the equation that the free energy of a certain lambda state is just the negative logarithm of the probability of accessing that state. And with the probability estimated using block histograms, in addition, the uncertainty of the free energy difference could be estimated using block bootstrap method. And in this figure, you can see that we compared alchemical metadynamics to long expanded ensemble simulations, where the benchmark is colored in blue. And as a result, for system 2, for system 1 and system 2, you can see that 1D alchemical metadynamics was able to correctly recover the free energy difference. Additionally, with the dihedral angle as the configurational CV in system 2, the 2D alchemical metadynamics also could predict the free energy difference accurately. So to further validate the efficacy of introducing configurational collective variable in alchemical metadynamics, we also decided to design a system with an intermediate difficulty between system 2 and system 3. And this system was made by modifying the original state, the original system 2, and specifically for system 2, where there are two torsional metastable states, as you can see in the figure, we modify the topology to greatly increase the torsional free energy barrier between the two metastable states. With this system, we first performed expanded ensemble simulations starting from different torsional states, which led to statistically different estimate of free energy difference due to the insufficient sampling in the torsional space, as you can see in the figure. And in the figure, you can see that during the expanded ensemble simulations, the system could not sample all the values of the dihedral angle. We later performed 1D alchemical metadynamics, which produced similar results to expanded ensemble because they are theoretically the same. And right now we are currently running 2D alchemical metadynamic simulations starting from different torsional states, and we want to prove that these simulations can produce statistically consistent results, showing that the introduction of the configurational CV could prevent a system from being trapped in the configurational space. And currently, we are wrapping up this project by working on the sampling problem of system 3, and we expect that the introduction of configurational CV, which is the number of water molecules in the binding cavity, should greatly accelerate the configurational sampling of the system. Currently, we are once the project is done, we expect that the alchemical metadynamics can be applied to the sampling problem of more complicated protein peptide binding complex, as it is expected to be a more powerful method than expanded ensemble. So specifically, we could try to, like for a challenging problem, we could first try to use 1D alchemical metadynamics to see if that solves the problem. If not, then we could adopt higher dimensional alchemical metadynamics, and in which the configurational CVs could be either based on intuitions or experimental observations, or determined by machine learning based methods such as RAVE or SCOOP, which is actually another algorithm that I didn't mention in the presentation. And the CVs obtained from these machine learning algorithms are usually much better than the CVs based on experimental observation, which could make alchemical metadynamics even more useful. So at this point, I've showed you that existing advanced sampling methods can be improved by modifying the underlying statistical or physical methods. However, there are still several challenges when applying advanced sampling methods in general. First of all, the sampling methods tend to be highly code-specific and non-portable between platforms. And currently, there are various MD simulation engines or platforms available, but the compatibility between these platforms is not good enough. This has limited the flexibility and the innovation in combining different sampling methods or formulating new simulation approaches. And the second is that the traditional schemes for parallelization fails to scale for large simulations. And as you can see in the figure, with the current algorithm, the scaling could be poor given a large number of cores, since the increasing communication time between the computers also leads to additional computational cost. In addition, right now, the asynchronous calculations are not supported very well, which means that all the simulations in parallel have to be synchronized to communicate with each other. If one of them crashes, then the whole set of the simulation will crash as well. As a quick introduction, Scalable Adapted Large Ensemble of Molecular Simulations, or ScaleMS, is a software framework we are currently working on that aims to address these problems. So this framework can express sampling methods using an approach agnostic of specific simulation code and data types. It also supports adaptive and asynchronous execution of simulation ensemble. As you can see in the figure, different tasks might be finished at different time. And with a synchronous parallelization, the fastest computer have to wait until other jobs are also finished, which leads to an inefficient use of computational power. And but if we run the simulation in an asynchronous parallelization scheme, there is no waste of time, and the crash of one of the jobs does not influence the execution of other jobs. A good example that the asynchronous parallelization scheme could be beneficial is multiple walkers metadynamics, in which we can have multiple walkers sampling the same free energy surface by running the simulations on the multiple cores or nodes. And with this parallelization scheme, when the first computer finishes its job, it can output the data to an external file and continue its next job without waiting other computers. Then when the second computer also finishes its job, it can just access the external file to read the data and it needs for the second job to start working on its new job. This parallelization scheme is much more suitable for a large number of simulations in parallel, but is still under development. In a nutshell, the goal of ScaleMS framework is to make it easier to run complicated algorithms on a very large number of computers, with the belief that much improved advanced sampling methods and such a framework would greatly promote our ability to sample configurational space of flexible biomolecules, developing new advanced sampling methods, applying the ScaleMS framework, and investigate difficult biophysical problems with these advancements compose the three pillars of my PhD research. So this is the end of my presentation. I know it's very long, but thank you all for your attention today, and any questions are welcome.
Great talk.
Yeah.
Any questions? Okay, let's unmute ourselves and give a pause to the two speakers. So at this point, any questions? Good, go ahead.
Hey, Wei-Tse. Great talk.
Oh, hi.
Just a few questions, but the first one is so these candidate CVs, collected variables identified by the RAVE, is astonishingly interpretable for me. Could you explain from the equations or what's built in the architecture that makes them so interpretable?
Yeah, let me go back to the slide there. I'm not able to. Okay, yeah. A second. Okay, so I think this slide basically show the protocol of using the RAVE algorithm, and so let me see. So this is how RAVE works. You know that first of all, we run an unbiased simulation, just like the standard MD simulation, to monitor some candidate CVs. So we basically just calculate those CV time series in the first step. And then we use this time series as an input to the RAVE algorithm. And as I just showed, like there is a encoder and a decoder, and the goal was to minimize the error inside that neural network framework. So that's the second step. We basically trained the whole RAVE framework, and then so in the third step, so the third step is actually what makes the output CVs very physically interpretable. So in the second step, as I just mentioned, like when we minimize the difference between the reconstructed output and the input, we basically just train that autoencoder framework. However, the way that the data was compressed in the bottleneck layer might be very complicated. So basically what we do is that from what we get out, so we will get out an output CV from the RAVE algorithm, but we don't use that we don't directly use that CV output as our final decision of the collective variable. We instead compare the probability distributions of all the candidate CVs with this output CV, which is the CV that is like accurate but physically not physically interpretable. So we basically compare this accurate but not physically interpretable CV with physical CV, the candidate CVs, and we pick the CV that has the closest probability distribution with that output CV, and we basically choose that CV from the candidate CV. So mathematically, we measure the Kullback labeler divergence, like the equation you see in the third step. We use that to minimize the probability distribution of the candidate CV and the output CV. So the final output CV that we can get from the RAVE algorithm is still very physically interpretable, because that was basically based on the original candidate CV we choose at the beginning. So it could be like either one of them or like some simple mathematical functions of those collective variables. Does that answer your question?
That answers. Yes. Thank you.
Thank you. Thanks for the question.
Okay. Any more questions? I do have a very naive question.
No, there is no.
Maybe it's kind of stupid.
No, yeah. Go ahead.
So my understanding is this. So you have some candidate CV like X,
Yes.
Y, Z, and so that's just like 3-dimension. And now I'm saying, okay, after this machine learning process, I figure out what is the optimized, like what is the best CV as a linear combination of X, Y, and Z. And okay, my question is there a protocol to determine what is this initial guess? Like what will be the candidate CV you're going to pick? Because it looks like you're within that space. And what if you're picking what if your best CV is outside of this?
Yeah,
space?
that is actually a very, very good question. And I have exactly the same question after reading the paper that proposed RAVE. And in fact, that was actually one limitation of the RAVE algorithm. So the RAVE algorithm did not automatically tell you among like infinitely numerous CVs which one is the best. It can only tell you from the set of candidate CV that you define at the beginning. So one limitation of this algorithm is that you have to like decide a very large set of collective variables, and for the RAVE algorithm to tell which one might be the best. Yeah, but actually this set of I'm not sure if this is correct, but this is my assumption. Like to generate this kind of this set of candidate CVs, I imagine that we could just throw in a lot of CVs that either make sense to us or doesn't or don't make sense to us, because like RAVE algorithm will just discard the garbage information. It is able to filter out the useful CVs that could be most representative of the structures. So I would imagine like for example, for a system with a size of 1,000 atoms, we could imagine that there would be approximately 3,000 slow degrees of freedom. And I think that the like some kind of brute force solution would just be I feed all these 3,000. Although I think it could be kind of time consuming, I think. But
yeah, I was thinking like
a large set of candidate CVs and let the algorithm figure out which CV is useless and which.
I was thinking there should be some, I don't know, maybe there should be some group working on like based on our physical intuition. If I give you a protein, can you tell me what is that? What will be the possible candidate CV? I don't know. I was just like thinking maybe that's possible.
It is a hard problem to balance between the physical interpretability and the accuracy of the CV.
Yes.
Because I would imagine like in the real world, if you are investigating a protein peptide binding complex, it is nearly possible that only one or two variables would influence the motion of the whole molecule. I think it would be like very, very complicated. Like a lot of CVs will be combined in a very convoluted way to like influence the motion of that system. So I think it's a hard question. I think some of the groups are working on generating CVs with high accuracy but lower physical interpretability, and this group basically focus on the physical interpretability of. And but this is actually a very new paper. This paper was published last summer, so it's cool. Basically one of the most recent research in like improving the CV.
I am not familiar with the technicalities of MD, especially observables. But if the data set is in other fields like, I don't know, point sets or geometric stuff, then I think the TDA, the topological data analysis, has a something called a persistent homology, which might guide you through how like persistent features in the data set for learning.
Oh.
But I don't know if they can apply to your data or something. Yeah.
Yeah, that's interesting. I don't know much about homology. I mean, the only thing that I know about that is like homology modeling, which is basically like based on a certain sequence of amino acids, you are able to build the structure of another protein which has like high similarity with this sequence of amino acids.
Mm-hmm.
Yeah, but yeah, I'm not sure how that could be applied to.
I'm talking about the homology in mathematics. So like if you have a cup, like a drinking cup, then it has two holes, like in donut.
Mm.
Like a hole, and the other hole is a donut. So a donut or a cup has two holes, and then there's some way to extract the holes from data using persistent homology, and the holes are like a feature for the data set.
Yeah, I think that involves topology in mathematics, right?
Yeah, but there's a well-developed set of methods in if the data is point sets. It's like point clouds, like points in Rn, point clouds. Then there's a well-established method to find the holes. But I'm not sure about your data. That might be time series or something.
Yeah, that's an interesting point, I think. Yeah. I'm not sure about the answer though.
I actually have one more question, but that might be it might be a very basic one. So in one of the figures, you show that there's a state A and state B and state C, where the state A is like a usual state and state C is like a rare state. And you go over things like transferring A to B to C. And my question is, like given a novel system, a new system, how do you know there's a state C that's rare?
Basically, I would say that for most biomolecular systems, metastable states is like can be observed easily because metastable states are the thermodynamic states that have higher stability and lower free energies. So, for example, for a protein peptide binding complex, the metastable state would typically just the bound state and the unbound states. And the questions could be just made more complicated if there are multiple binding sites for the ligand. So you would imagine that there could be multiple bound states and multiple unbound states. So these states are the states that we could observe in the real world because, as you would imagine, for the rare states, it is hard. They are like hardly observed. So that's the way we know the state. So we know what bound state look like. We also know what the unbound state looks like. But the point is that we want to collect the data from both these states in just one simulation. And it is not easy with a traditional molecular dynamics simulation.
I see. Thank you. This is a domain-specific answer that I wasn't aware. Thank you.
Thanks for the questions. Those are very good questions. Yeah.
So if there's no more question from the audience, and let's thank the speaker again.
Yeah, thank you all for your time.
I will pause recording right now. I'll stop recording right now.